Yeah.
This meeting is being recorded.
Yeah. That is correct. Yeah. If you just look at the two definitions, you will see why it is the same. Because ax minus rho x greater than or equal to 0 means rho should be less than or equal to axi upon xi. But you are taking just the, you are not taking very small rho. You have to take just so that it is the exact minimum. You look at these two definitions, this definition and this definition. It will be clear. Because I have to say rho is the largest number. Because if rho is not the largest, then what will happen is that this will be strictly positive, and then I don't get f(x) equal to, right? Is it okay? Yeah.
Yes, sir.
Okay.
Yes.
Okay. The next result is, if x is non-negative vector, non-zero vector, and define y to be the in plus a raised to n minus 1. We know that from the earlier result, we know that this matrix is positive, strictly positive, times x. Then f(y) is greater than or equal to f(x). Okay, I think I'll prove this. So just one line is enough. So if you look at ax minus f(x) times x, by definition of f(x), this vector is non-negative. By definition of f(a). Just by the definition of f(a). Now multiply both sides by in plus a raised to n minus 1. So if you multiply both sides by in plus a raised to n minus 1, last time I said that because this matrix is positive, inequality is maintained, minus in plus a raised to n minus 1 times x, that is greater than or equal to 0. And now the result is clear, because this by definition is a times y. This is nothing but a times y. And so a times y is greater than or equal minus fa. This is nothing but f(x). Yeah, I think there's a small problem here. Here I should also have fa. Sorry, fa(x), not x, but fa(x). Just multiply both sides by in plus, multiply this on both sides by in plus a raised to n minus 1, and the result follows. This proof is also straightforward. Okay, so what we have done here is, when you take a vector x and then go to in plus a raised to n minus 1 into x, the value of fa increases. Maybe not strictly, but it increases. Okay, the next two results I think I'll state without proof. The next result is actually not that difficult, but you can look up. So the next result just says that fa is bounded. Fa is a bounded function over En. And here I just want to state one observation also. And the following result also I'll state without proof, that fa attains maximum on En. Okay. So the first is number 9 is quite easy actually, but although I'm not writing it down, it's quite easy that FA is bounded. Number 10, you have to work a little more because En is closed. En is a compact set. And if you have a bounded function on a compact set, it will attain a maximum. But how do you know that the maximum is not on the boundary? And that is why this requires a proof. And actually, there are examples where FA may not be continuous on the boundary. There's a simple 3x3 example actually, but I'll omit that. But some technicalities are there. But all I'm saying is the subtle point here is that FA is continuous if you restrict yourself to the interior of N. There's no problem because all the operations are continuous. But when you start going to the boundary, then zeros come. And then it is not clear. It's actually not true that FA is continuous on the boundary. And so we cannot immediately say that it attains its maximum, but this can be proved that FA attains its maximum on En. So now we will get hold of that maximum, and then we can actually prove the Perron-Frobenius theorem, the first one or two parts, by using these results. That means, let me now show just a argument that, so the next result is that A is non-negative irreducible n by n, then so the first statement of the Perron-Frobenius, then A has a positive eigenvalue. Now I'm going to call it R because it is also the spectral radius, so there's no harm in calling it R. And with a positive eigenvector. Earlier we proved this for positive matrix. And R is the spectral radius. That means R is greater than or equal to mod lambda I for any eigenvalue lambda I. This part, the proof is very similar to the earlier one, the last statement. So I will not give the proof here. But the first statement, I think I'll just tell you the proof because it follows from the earlier result. So we know that FAX attains its maximum. So there exists X naught such that FA has its maximum. That means at X naught. That means FAX naught greater than or equal to FAX for all X. X naught is also in En. And FA attains its maximum there. So that maximum value, as I made a remark earlier, that turns out to be the Perron eigenvalue. So but we have to prove it. So let R be that maximum. And I will show that R is an eigenvalue. And with an associated eigenvector, positive eigenvector. Okay, so suppose R is that. So another way of writing R is that the equivalent, the same thing. R is the maximum of FAX. X belongs to En. Same thing I'm rewriting in a different way. Okay, so it's very easy to, first of all, to show that R is positive because R is greater than or equal to FAX for any X. So I will take X to be the vector 1, 1, 1. Take X to be the vector 1, 1, 1, or 1, 1, 1 transpose, actually, column vector. So if you look at the definition of FA, this comes out to be the minimum row sum, because AX will then be the row sum vector. So this will be the minimum summation Aij over I. And that is definitely positive.
Don't we X from En?
Actually, sorry. Actually, that is where I use the first result. I take, it's a good question, that I take 1 upon n. But Fa is homogeneous. Okay, Fa is homogeneous, so it doesn't matter.
Oh yeah,
So now,
that's
okay. Yeah, but this is a correct, we have raised the correct point. But I can take 1 upon n dot 1 upon n. Then it will be the 1 upon n times the row sum. And A is irreducible, so no row is 0. So the row sums are all positive. So this is definitely positive. Okay. Now to show that R is an eigenvalue, I'll just use the earlier results. So now we will start with the fact that AX naught minus Rx naught is greater than or equal to 0. That we know. And I claim that it is actually equal to 0. That means X naught is actually an eigenvector. So suppose not. So suppose Ax naught minus Rx naught is not equal to 0. Now by the earlier result, I plus A raised to n minus 1 multiplied by Ax naught minus Rx naught is strictly positive. That we showed in one of the earlier results. And there was a definition of y, so that now that I'll call it y naught. So when you open this up, I plus A raised to n minus 1 multiplied by x naught, that I'll call it y naught. A commutes with it, so no problem. So I get A times y naught. So y naught, what is y naught? Y naught is I plus A raised to n minus 1 times x naught minus R y naught is positive. So here y naught is I plus A raised to n minus 1 x naught. Now, if I just add a small epsilon to R, then because it is strictly positive, I can just perturb R a little bit by a small epsilon, then it will be still positive. So epsilon is positive and small, which means that by the equivalent definition of Fa, this means that R plus epsilon is less than or equal to Fa y naught. This was that other definition of Fa that I gave in one of the earlier results. And so this is true for every positive number, epsilon. It's a small positive number. And so then you get R, which is less than R plus epsilon is less than or equal to Fa y naught. But this contradicts that R is the maximum such value. Because R was the maximum such value. If you go back to this equation here, that we have been seeing earlier also, that R is the maximum real number. But here I have shown that R plus epsilon also satisfies the same thing. That's a contradiction. And that contradiction has come because of this assumption. Okay, so this is contradicting the maximality of R. Okay, I think if it is not clear, you can just think about it. But these are not technical proofs, these are simple proofs that I am presenting. I hope this is clear. Because I am contradicting the maximality of R. And so, and then it follows that x naught is an eigenvector, because now we have shown that this claim is proved. And so we have also shown that A has a positive eigenvalue and x naught is definitely in En. So x naught is non-negative. And very long back, we have seen that such an eigenvector must be positive. So we have shown the two assertions that A has a positive eigenvalue and a corresponding eigenvector is positive. And earlier this was shown for a positive matrix. Now we have shown it for an irreducible matrix. And the next assertion that R is the spectral radius, that proof is very much identical to the earlier proof. That means if lambda is another eigenvalue of A, then mod lambda is less than or equal to x naught. So I will not give that proof. That is very similar to the earlier proof. Okay, so this completes the other assertion. And then, as I said earlier, the geometric multiplicity equal to 1, that is also very similar to the earlier proof. And the algebraic multiplicity, I am not doing it, as I said, that's a bit technical. Okay, so that is about irreducible matrices. And now I want to go to some refinement of irreducibility. So, as I said, I gave this example that a matrix may be irreducible, but any power may not be positive. So now we want, so irreducible matrix, there is a positive eigenvalue, and earlier and that is the spectral radius. So if we take the eigenvalues, so A is irreducible, n by n. And if you look at the eigenvalues in the complex plane, so far we have seen that this number is an eigenvalue, the spectral radius. And there are other eigenvalues on the boundary. And if A is positive, actually it will turn out that there are no other eigenvalues. And this has a very high relationship with graph theory, directed graphs. And this work is the heart of what Frobenius did. So let us look at this full cycle matrix. That's a good example to start with. So I want to tell you the exact number. I'm concerned about the eigenvalues on the boundary. And so let me make one definition that if there are k eigenvalues on the boundary, that means k eigenvalues satisfy mod lambda is equal to the spectral radius, then that is called so first of all, there are two definitions here which are important. One is that of a primitive matrix. So, and because of that, we are going to call it the index of imprimitivity. So suppose there are k eigenvalues on the boundary, or let's say suppose, so R is, I'll now always use R for the Perron eigenvalue. So this number is R. And suppose there are H eigenvalues, exactly H of modulus R. These are complex of modulus R. So H is the number of eigenvalues on the boundary of the circle, the spectral circle, so far. And we call H index of imprimitivity, or sometimes simply index. But this has nothing to do with the usual rank index. That is a different index. Imprimitivity. And why it is called index of imprimitivity? Because of the other definition, that if h is equal to 1, that means there is no other eigenvalue other than the spectral radius on the boundary, then A is called primitive. And that is why this is called, so A is called primitive. And if A is not primitive, then it is imprimitive. And that is why we talk about the index of imprimitivity. So primitive is a stronger condition than irreducibility. And this full cycle matrix is again the classic example of something which is irreducible, but not primitive, because it has two eigenvalues, 1 and -1. 1 is the spectral radius, but -1 is the other eigenvalue with modulus 1. So here the index is 2. And similarly, if you take the full cycle matrix of order 3, then you get again, if you take, this is irreducible because the graph is a full cycle. There's no question about strongly connected. You can go from any vertex to any other vertex. So this is definitely irreducible, but it is not primitive, because if you take powers, then as you know, the cycle will keep moving, but it will never become. Okay, that is not because of the other result I'm going to state, but this is not primitive. And as you know, the eigenvalues are the cube roots of unity. And so there are 3 eigenvalues. So the index is 3. Okay. So now we enter into the strongly connected graph in a much better, much deeper way. So the circuits. So what are circuits? Circuits, I mean, circuits are some also called cycles. So if you have a graph, and if you have something like directed graph, then this is the, so there may be some other edges also, but this is a cycle of circuit or cycle. I'll use the same term of length 4, and there may be some other edges. This is not strongly connected, but this is a circuit of length 4. And so that this matrix, the graph has a circuit of length 2. So this number h has a very interesting graph theory connection. And actually there are 2 or 3 equivalent ways of stating what this number h is. So I think I'll state 3 ways of, and here I'm going to go completely without proof, but because this is the work of Frobenius, which is not at all easy. It's not easy means you have to work at it. I mean, it's not something you cannot understand or anything beyond your reach, but you will have to take the book and follow these proofs. But I'll state 3 descriptions of H, index of imprimitivity. So the definition is, what is the index of imprimitivity? It is the number of eigenvalues on the boundary of the circle with radius r. So the first result is just if h is the index of imprimitivity, and okay, let me not state the first result. It's not a direct. So I think I'll state at least 2 different definitions. So first of all, if you take this eigen, so suppose h is the index of imprimitivity, or let me simply call it index. So that means there are h eigenvalues of modulus R. Eigenvalue of modulus R. Then these are the distinct roots. Actually, the next statement will follow from this statement. These are the distinct roots of R to the power h. As you know, any complex number, I mean, you can talk about at least the unity, there are roots of unity. Similarly, any complex number you can talk about. If you take a complex number by the fundamental theorem of algebra, if you take any complex number, then it will have n roots by this equation. So you take the roots of R to the h and look at the distinct roots, then those are the eigenvalues. But this is giving us an important conclusion about the location of these other eigenvalues. What it is saying equivalently is that if you again go back to that picture of eigenvalue, and if this is the spectral radius, and if h is the index of primitivity, then you know the roots are symmetrically located. So the other roots are like the vertices of a polygon, because other roots cannot be arbitrary. So this is not a good picture, but those are the distinct roots of R to the h. So in other words, if you rotate the disk by an angle 2 pi upon h, then you again get the same set. That is the same property, because these are the distinct roots, and using the description of roots of a complex number, the geometric description of roots of a complex number, we conclude that those are exactly, if you rotate it through 2 pi by h, but not through any smaller angle. So the rotation should be by 2 pi by h. Smaller angle will not do the job. For example, this matrix has two eigenvalues, 1 and -1, and you need to rotate through 180 degrees to get the same set. To get the same set of eigenvalue, but not through a smaller angle. So 180 degrees, because it is 2 pi divided by 2, so which is pi. So you need to rotate it through 180 degrees, and then you get the same eigenvalue. Okay, but there is another very surprising, another conclusion, that we have not talked about the eigenvalues inside the disk. So inside the disk, there are eigenvalues. There may be eigenvalues. Of course, if you take the full cycle matrix, then these are the only eigenvalues. But for an arbitrary non-negative irreducible matrix, there will be other eigenvalues. But it turns out that the set of all eigenvalues on the boundary as well as inside, that is also invariant with respect to rotation by 2 pi upon h. That needs a further proof, and we will not require it much, but that's another fact, that all the set of eigenvalues, they go over itself by rotation through 2 pi upon h. Okay, now I will state one more, or rather two more definitions of equivalent definitions of h. So one definition of h is that it is the number of eigenvalues of the same modulus. Okay. So the next definition is, which is a very graph theoretic definition. So consider cycles or circuits in the graph associated with A. So A is an irreducible matrix. I take the graph associated with A, and I claim This is a completely geometric way of describing H. H is the greatest common divisor of all cycle lengths in GA. Very subtle definition and very deep property. It requires, definitely the proof is non-trivial. So you look at all the cycles in GA, length means the number of edges. So there may be cycles of, there may not be any loops. Suppose there are no loops. So this also says that if there's a single loop, this is stating one very important, but first let me illustrate this. So when we go to the full cycle matrix, there is only one cycle. And so of that length. So suppose this is k by k, then there's a cycle of length k and no other cycles. So the GCD will be k, and there are k eigenvalues we have already seen. But if it so happens if that there's a cycle of length 3 and in the graph, and also a cycle of length 4, then also because they are relatively prime. So suppose this is the graph associated with A. Clearly it is strongly connected. And there are two cycles. Of course, the graph can be more complicated. Okay, they need not be disjoint or anything. But suppose there are two cycles, one of length 3, one of length 4. So 3 and 4, the GCD is 1. And so H is equal to 1. Sorry. Yeah, so here H is equal to 1. There's only one eigenvalue of modulus 1. But if it so happens that there is a cycle of length 3, and suppose there is another cycle of length 3, and suppose there is a cycle of length 6, suppose there is a cycle of length 6, then there are two cycle lengths. One has length 3, one length is 3, one length is 6. Their GCD is 3, and so this will have index 3. So it will have 3 eigenvalues of modulus equal to the spectral radius. So the GCD of all cycle lengths is the index. So this is the fully graph theoretic definition. And now there is one more. Yeah. Yeah.
Number of vertices for this graph will be basically the order, right?
Yeah. The order of the matrix. Yeah.
Yeah.
Okay. So there is an equivalent algebraic definition. The two are related actually, but where I don't need the graph. And so let me state that definition again without proof. Yeah. Okay. So suppose A is irreducible and suppose index is H. So we have already seen that so consider the polynomial, the characteristic polynomial, whatever it is, I can rewrite it in the form lambda to the power n. It's a monic polynomial. So this is the characteristic polynomial plus the other numbers a1, some coefficient n1, because other coefficient will maybe 0, plus a2 lambda to the n2 dot ak lambda to the nk. So these are the terms, and let me assume that here n1 is greater than n2 I can assume that without loss of generality, and a is n by n. So the characteristic polynomial will be of this form. There's no assumption here. It will always be of this form because the largest coefficient is 1. So the first leading term is lambda to the n, and there are other terms. Then you look at, so here is one more purely algebraic description of H. So H is the GCD.
Why do you take this form whether the power of lambda is are n1, n2, and nk? Why can't we take general that it's in some n degree polynomial with the coefficients may be 0?
Yeah, when the coefficients are 0, I'm not writing that term. That's all.
Okay.
I'm only writing the non-zero coefficient. Others are 0. That I can always do.
Yeah. Fine.
So there is no assumption here. Okay, so you take the GCD of n minus n1, the integers, n1 minus n2, because these are decreasing sequence, these are numbers are positive. n1 minus n2 dot nk minus 1 minus nk. And that turns out to be also index of impermeability. So as you can see, this has some similarity with the earlier definition. There it was the GCD of cycle lengths. I'm not saying that these are the cycle lengths, but it turns out that the GCD of these numbers is also equal to the index of impermeability. Yes?
Yeah.
Any question? Okay, so these are two different ways of describing the index. One was the GCD of cycle lengths, and one is this GCD of these differences of
Sir,
coefficients.
Sir,
Yeah.
if there's a graph which say, from the previous example, I thought if there's a graph which has three separate blocks, on in each of the blocks there is a cycle of length 3. Then there are three spectral there are
No. But by blocks you mean these kinds of things. What do you mean by blocks? That means the two connected. That
no,
means,
not connected. Yes,
no.
disconnected.
Huh?
Yes,
what-
three disconnected.
No. It can. First of all, the matrix is irreducible, so there's no question of disconnected. Okay, the matrix is so far irreducible. So primitive is a stronger concept than irreducibility, because the matrix is irreducible. It definitely, even if you look at the underlying undirected graph, it is connected.
Okay.
Okay, so there's no question of three blocks. But I'm going to come to such matrices when we come to reducible matrices.
Yeah. Can you give intuition or some motivation about this result? How do we approach this? Like,
No.
you come up with this thing.
No intuition. I don't have intuition. This is the typical work of Frobenius. That is how Frobenius has worked. Unfortunately, I don't really understand why this is connected to I have seen the proof myself. Now I don't remember, but so I don't really have any intuition here. Why this GCD is the same as the earlier GCD, and this is a typical feature of the work of Frobenius. Okay. But if you read the proof yourself, which is easily available, then maybe you will understand more, because the proof technique, there are some similarities and you may get some intuition. Okay, now one simple corollary of these results is that if you have an irreducible, like earlier we saw that if there's a loop, if the graph has a single loop, then there's a cycle of length 1, and then immediately the GCD becomes 1, and then the index becomes 1. So more generally, so that means if you have an irreducible matrix, but it has a loop, that means trace is positive, because if there's a loop, there may be more than one loops, then the trace is positive, then it implies H is equal to 1. So that is one simple case. So it is primitive. So an irreducible matrix with positive trace or a single positive diagonal element is sufficient, and that will be the index. Yeah, I was mentioning that there is one more definition. So I initially said 3 definitions. I was not remembering. So there's one more definition of one more way of describing the irreducible, the index of impermeability. And so let's go back to this example. the 2 by 2 example. The problem with this example is that if you take powers, it never becomes positive. So let us look at, let's take an irreducible matrix and let's look at minimum k such that if it exists, a to the k is strictly positive, then okay, I think I will not go into that connecting it with the index, but all I want to say is that if there exists such a k, then we will say that a is power positive. That means some power is positive, and it will turn out that it is also primitive. So I think this minimum has no meaning. Suppose there exists a k. I was going to make a definition, but suppose there exists a k such that that power is positive, then a is primitive. So primitive, one more way of, so earlier we saw that in a strongly, yeah. Is there a question?
Yeah, I am asking, will such a k always exist?
No, because this example is in front of you. So otherwise, we just say that if it exists, let me say if, otherwise it is imprimitive. As we have seen that, yeah, it may not exist because for this 2 by 2 example, it doesn't exist. It never becomes positive. Then the only thing is it is irreducible, but it is not primitive. But if there exists such a k, then it is primitive. That's what I'm saying.
Yes, I got it.
And actually, this is not very difficult to connect it with the earlier definition, because if there exists such a k, then if you look at the circuit lengths, their GCD will be 1. Just think about it. So it's not very difficult to connect this with the earlier definition.
Yes, sir.
Okay, so now,
Hello, sir.
Yeah.
Excuse me.
Yeah.
So actually, I have a doubt. In the definition of primitive, do we need the matrix to be always irreducible?
Yes. I keep saying that primitive is a stronger notion than irreducibility. So let me actually show you what we have done graphically, that means by a diagram, that this is suppose this is the set of non-negative matrices, n by n non-negative. Then within that, we have divided into two groups. One is reducible, one is irreducible. And within irreducible, we have divided into several groups: index 1, index 2, ... index. Actually, I think the maximum will be n minus 1, because the GCD of, by any of those definitions, you can see that the maximum is n minus 1. So we have divided irreducible into further groups. And this is the class which we are calling primitive, index 1. And this is the class we are calling imprimitive. So that is what we have done. Okay. So now let us look at.
Well, sir, just one more question.
Yeah.
So, thinking about non-negative matrices is easier, visualizing. Is there any intuition to come from non-negative to reducible and irreducible?
Yeah. That intuition is through the like Markov chain or graphs, because having access. So that is not difficult. That intuition is not difficult, because you are coming to access of one vertex to another vertex. So in the graph, from any vertex, you can go to any other vertex by a directed path. Then it is irreducible.
So, sir, the first definition of irreducible was via graphs, or
that was via partition matrix, but that equivalence is not difficult. That was via partition matrix, that there exists a permutation. I call it reducible if by a permutation matrix, you can put it in this form. And then I call it irreducible if it is not reducible.
Okay.
But it is not difficult to connect this definition with the graph theory definition.
Okay, sir.
Okay, so now, so suppose we take a non-negative matrix. Then first of all, if you have a non-negative matrix, and if the graph, you look at the graph strongly, yeah.
Does the book of Mink, that book non-negative matrices, contain the proof of all the work of Frobenius?
Whatever I am doing, whatever I stated so far, that is done in that book, yes.
Okay. All the proof are also there.
Yeah, the book by Mink, because that is, I found it easier to read. Other books also contain the proofs.
Okay.
I wasn't able to find the book online, sir. So could you?
No, but I got it online by issue, but it is available online. Earlier it was not available, but last time I showed you the copy, so it is available.
Yeah, you should. Yes, okay.
And my book with Raghavan also contains all these things, so that you can read also, but that is like further reading. It has many other topics, but I think you can also take a look at that book.
Okay, sir.
But to study the proofs, you can use Mink's book. Okay, so now, so suppose you take a non-negative matrix, just without any assumption, and then look at the graph associated with A. So A is non-negative only, and look at the graph. This is the directed graph. If you look at the underlying undirected graph, and if that is not connected even, then we can sort of do a permutation and rows of rows and identical permutation of columns, so that you get this form. There will be a 0. This is when the underlying undirected graph is also not connected. Okay, so what we can do is we can look at the B and C separately. And so I can make the assumption that A is non-negative, but the underlying undirected graph is connected. That is not a big assumption, because I can deal with B and C separately. So we can do this. So now we can reduce it. So I'm assuming it is reducible. So after a permutation of rows and identical permutation of columns, so I'm assuming that A may be reducible, then you get this form. Okay. Now here B and D they may be reducible, they may not be reducible, or they may be irreducible. So I can do this further on B and on D, and I'll get a further partitioning. So ultimately you can put it in a certain canonical form. Sometimes this is called a Frobenius canonical form, but there's also another Frobenius canonical form. So we'll just call it canonical form, that any reducible matrix, you can ultimately put it in this form. A11 block upper triangular. And here, all the diagonal blocks, so there is something here. This is not 0. Okay? This is just obtained by repeatedly working on those matrices B, D, and so on. So here each AII is either 1 by 1, because 1 by 1 we are always calling it irreducible, or irreducible. And that's a canonical form. So any non-negative matrix, of course, I'm assuming that the underlying undirected graph is connected. If it is not connected, you have to work with those two blocks, but it's not a big thing. So it's not a big assumption. So any non-negative matrix can be put in this form. So this is very much of interest in the theory of Markov chains. We can talk about access. That means, so these stars may be zeros also. So what I can do is I can talk about paths in the directed graph. I can look at say AII, and if there's a path from, suppose there is AII and then there is A. So suppose there is A11, A22, then there is AII, and then there is AJJ. So I will see that J has access to I if there's a path in the directed graph from J to I. That will depend on the zeros, non-zeros here. So that is how we define. So there are K classes. So there are sort of K classes. The vertices can be partitioned into K sets. The graph is strongly connected. The graph is connected, may not be strongly connected. So there is no, so there are edges here also. So these are the classes. This corresponds to A11, this corresponds to A22, and so on. And if you can find a path from here to here, then this means 2 has access to K. Class 2 has access to class K. So that is how we define access. So let me show you one result which is a very graph theoretic result, and it uses this access notion. So let me take a non-negative matrix. Let me first take a very simple non-negative matrix. Here actually I am taking, so you can imagine that this is a non-negative matrix, but actually the diagonal, so here A11, A22, they are all 1 by 1 in some sense. I mean, those are the classes, because this is not irreducible, by the way, because from the first vertex, you cannot go to the second vertex or the third vertex. Actually, if you look at the graph, then this is the graph. So all the loops are there because diagonal elements are positive. And from the second, you can only go to second. From the third, you can go to 1 as well as to 2. So this is the underlying undirected graph is connected. Okay. So what are the eigenvalues here? The eigenvalues are the diagonal elements 2, 5, and 3. 2, 5, and 3 are the eigenvalues. But now I am interested in only those eigenvalues which have a non-negative eigenvector. Because for an irreducible matrix, we have shown that first we showed it for a positive matrix. That for a positive matrix, if there is an eigenvector which is non-negative, it must correspond to the spectral radius. And the same thing essentially we did for irreducible. But this is reducible. Like if you take the identity matrix, if you take a diagonal matrix, suppose I don't have this, suppose I just have a diagonal matrix, then all the eigenvalues have non-negative eigenvectors because these are eigenvectors 1, 0, 0, 0, 1, 0, and so on. So those are non-negative eigenvectors for all the eigenvalues. So in general, there can be other eigenvalues. The spectral radius is 5, but other eigenvalues also have non-negative eigenvectors. So now I'm asking which eigenvalues have non-negative eigenvectors. And I claim that okay, so I claim that not all eigenvalues here, 2, 5, and 3, they have non-negative eigenvectors, but so I think here let's look at the. Okay, so I think I should take maybe the other way around. That means the result I want to state, maybe it is more convenient to take in the, because this it depends on the access property. So let me first take a 2 by 2 matrix. I think it is easier to do it first for a 2 by 2 matrix. So I'll come back to this 3 by 3. Actually, there's going to be one homework problem today, and that will require this kind of access property. So suppose I take a 2 by 2 matrix, but not a diagonal matrix, but a triangular matrix. Suppose I take, now if I take 1, 0, so the eigenvalues are 2 and 3. then this is, so this is not an eigenvector. So I'm asking, is there an eigenvector for 2? This is not equal, this is equal to 5. This is not a multiple of 1, 0. So let us work out the eigenvectors. So what will be the eigenvector for 2? So I get the equations 2x is equal to 2x, which is always true. And then I get the equation 5x plus 3y is equal to 2y, which means 5x plus y is 0. So as you can see, if the eigenvector has to be I want non-negative eigenvector, then a non-negative eigenvector here will not exist because of this second equation. Because if both are non-negative and the vector is a non-zero vector, then this cannot be 0. So why it is happening? So it is happening because this 3 is greater than 2, and that is causing the problem. So but for 3 there is no problem. For 3, the eigenvalue 3, I can take, so suppose we try to work out the eigenvector for 3, then I want 3x and 3y. So that tells me that 2x equal to 3x, that means x is 0. And then the second equation works out automatically. 3y equal to
1 0 eigenvector.
1 0 or 0 1?
0 1, sorry, sir.
0 1. So that it exists. So those actually those eigenvalues. So we have to, because this is happening because, so the last number, so the last number will, yeah, I think I'm trying to see whether it is this form or should I look at the lower triangular or the upper triangular. Yeah, actually I kept saying upper triangular, but these are lower triangular. So maybe I should look at upper triangular. So anything which is, okay, I think I'm going to state it, but it is not very accurate. You have to check it. I think I'll give the exact formulation. But let us go back to the general matrix. Okay, so we first put it in Frobenius form. And so which eigenvalues have non-negative eigenvector? So first of all these diagonal blocks are irreducible. So you look at their spectral radius. That means you look at the spectral radius of A11, spectral radius of A22, and so on. So these are the possible candidates. That means only, by the way, these are also, as you know, any eigenvalue of a block, diagonal block, is also an eigenvalue of the whole matrix. So these are the only possible, the eigenvalues of A are the eigenvalues of A11, A22 put together. So these are definitely eigenvalues of A. And these are the possible such eigenvalues, but not all of them. So it is like reducing it to a diagonal matrix. You take a diagonal matrix where on the diagonal you put RA11, RA22, dot, dot, dot. And outside the diagonal, if it is a star, you put a non-zero number. Doesn't matter which non-zero, because ultimately it depends on the graph. And if it is a zero matrix, then you put a 0. So ultimately it will turn out, so yeah, here this is where I have to check the exact result. But RAII, so RA11, spectral radius of A11, spectral radius of A22, these are the possible eigenvalues which may have a non-negative eigenvector. No other eigenvalue is going to work other than these eigenvalues. But these eigenvalues themselves are also not all going to work. So RAII has a non-negative eigenvector if and only if any k with RAKK greater than RAII, any such class has no access to I. This is where I have to little bit, because I'm concerned about whether I should consider the lower triangular or the upper triangular. There's a similar upper triangular Frobenius form. So I may have to correct it, but this is essential statement. So it depends on access properties. And so I'll check it myself and tell you maybe tomorrow. But in the meanwhile, you can work out that example. So if you go to a 2 by 2 matrix, and like we had 2, 0, what you put here is not important as long as it is non-zero. And suppose it is alpha. So the eigenvalues are 2 and alpha. Alpha definitely has a non-negative eigenvector because the vector 0, 1 will be an eigenvector. But whether 2 has a non-negative eigenvector, like earlier we worked out that example, that depends on whether alpha is greater than 2 or alpha is less than or equal to 2. Because when alpha is 3, we saw that it doesn't work. And so it all depends on the numbers which are greater than 2 or less than 2. And this we can generalize to a, like this example essentially can be generalized to the case where there are only 2 blocks in the Frobenius normal form. That means I have a matrix which is irreducible, but after a permutation, suppose I am able to put it in this form, where A11 and A22 are irreducible, only 2 diagonal blocks. Then RA11, spectral radius of A11 and spectral radius of A22. These are the only eigenvalues of A which can have a non-negative eigenvector, and R of A22 has a non-negative eigenvector always. I'm not proving it right. But actually, it is not difficult because why this is true? Because A22 is irreducible. So A22 has a non-negative eigenvector. So if you take the partition vector, I'm imitating the 2 by 2 example. So if I take a 0 vector here and a Perron vector of A22, that will work out to be an non-negative eigenvector for A. So this statement is not difficult, that the spectral radius of A22 has a non-negative eigenvector. And spectral radius of A11 has a non-negative eigenvector if and only if, like the 2 by 2 example, if and only if RA22 is less than or equal to RA11. This was like the 2 by 2 example. Otherwise, it will not have a non-negative eigenvector. So this is sometimes called, if you look at Google and look at Frobenius Victoria theorem. This is essentially called Frobenius Victoria theorem. And this is interesting because one doesn't usually think that such things will depend on the underlying graph. So I think in today's homework sheet, there is one such problem, and I think that statement I said may not be completely, you can fix that statement. If you work out a couple of examples, I suggest that you work out 3 by 3 examples. So you take a 3 by 3 example where it is lower triangular, these numbers are positive, and these numbers are kind of arbitrary, and you try to see which of these have a positive eigenvector. And then you will understand by just looking at the characteristic equation and trying to solve the characteristic equation, you will understand that graph theoretic result. Okay, so I think I've touched upon most topics. I've left out many topics, like as long as Perron-Frobenius series is concerned, I have left out inequalities for the Perron eigenvalue. And for example, there are many inequalities starting with if A is non-negative, B is non-negative, and if A is greater than or equal to B entry-wise, then Perron eigenvalue of A, or R of A, is greater than or equal to R of B. So the proof is not difficult. One proof is at least very easy. You multiply by, take the eigenvector of A and multiply on, and take the left eigenvector of B and multiply on the left. So I can make this inequality. So here X is the right eigenvector of A and Y is the left, Y transpose is the left Perron vector for B. And if you simplify this, you will get R of A Y transpose X greater than or equal to R of B Y transpose X. And then you can say that R of A greater than or equal to R of B. One more important result, if you take a matrix A, for these inequalities, you can always assume without loss of generality that the matrix is irreducible or even positive, because like for this result, I could have assumed that A and B are positive, because for non-negative, then it will follow by continuity. So similarly, if you take any principal submatrix of A, say A11, principal submatrix, then the Perron eigenvalue of A is greater than or equal to Perron eigenvalue of A11. And in particular, it follows that Perron eigenvalue of A, which I stated last time, is greater than or equal to any diagonal element. So there are many such inequalities for spectral radius. There are further inequalities, which I have not stated. So on Perron-Frobenius, what I have done so far, if there's any question. So next time I want to tell you about one related topic. This is an area which is related to non-negative matrices, but it has gone into many other things called matrices over max algebra. So I'll just introduce the eigen problem over max algebra next time. And in one lecture, you may not get the full flavor, but I try to at least tell you the basic. And yeah. So next time I'll give you the basics of max algebra. So Perron-Frobenius, if there are any further questions, you can also ask either in this afternoon or next time. Okay, so I think I'll stop for today.
That's it.
Thank you, sir.
Yeah, any question?
Sir,
Thank you.
actually, you said the paper, no, sir, by Crane Millman.
Yeah,
You
yeah,
say
yeah.
the title of the paper.
There are a series of papers actually. So, but somewhere it is mentioned. So yeah. So let me say that somewhere in the title you will find matrices leaving a cone invariant. I am not, because the original papers are in German perhaps, so I am not aware. But they have a series of papers. So matrices, just Crane and leaving a cone invariant. But I will suggest you another reference instead of going to the papers. There are 2 volumes on non-negative matrices by Gantmacher. These are a must if you want to volume 1 and volume 2. Again, these may not be available online. These are old books. First edition came up in the, again, not in English, the first edition, 50s or something, but there's the English edition and I think it's also revised or something. But these volumes are definitely, you must see them for Perron-Frobenius theory as well as for the work of Crane-Millman. So these are better references than the original papers. Okay, any other
Sir,
question?
could we please repeat the author name, non-negative matrices, volume 1 and volume 2?
This is the name, it's hard to pronounce. Gantmacher,
Okay.
German. Okay, so I think.
Thank you so much, sir.
Okay.
Thank you, sir.
Yeah, you can stop the recording.